.075 meters. The other end of the rope is attached to a .67 kilogram mass. Is the tension in the rope the same on both sides of the pulley? If not, which side is the greatest tension? Yes?
I'm looking for Mr. Kaiser.
Oh, I think she went down to her lunch.
Gotcha, thank you.
If not, which side is the largest tension? Find the tension in the rope on tension rope on both sides of the pulley. Okay. So we got a picture that looks something like this. We pull down with a force of 25 newtons. Pulley has a mass of 1.3 kilograms and a radius of .075 meters. Over here, we have a little bitty .67 kilogram mass hanging. Okay. So first question we have is tension on the right the same as the tension on the left?
No.
What's your answer then?
No.
No. Why?
The force on the right has to support both the weight of the pulley and the weight of the pulley.
Well, not support, but it has to move the pulley and move the other thing. Okay? What's the rule here? If that pulley has what? Mass, the tensions are not equal. If the pulley didn't have mass, and you will see, and you guys can see problems of both types. If the pulley had negligible mass, the tensions would be equal. Okay? So now, we know this one's going to be greater, and now they want us to find the tension. Okay, so we start, we go to work on this problem, so to speak. If I was going to start working on this thing, I might call this little m, and you have little mg pulling down. You have the tension on the left going up. You have a bad Valentine's Day show coming over the intercom. No, it was.
It was terrible.
I hate the buck shows.
Alright. That was a fine show. Okay.
Same.
A determined Valentine's Day.
Don't you turn me on.
Okay. So anyway. That tension, as I've gone through today, we've really been struggling with this tension piece. And the tension pulls up on the mass, but the same tension pulls down on the pulley. Okay? Okay, you come over here. We got the tension on the right pulling down. If you want to go ahead and throw in some more forces, I'll use big M to represent the pulley. So you got its weight coming down, the force of a support going up. If I was trying to engage this problem, I would start right here. And I would start by summing forces. So I have the tension on the left going up, minus the weight going down. Whenever you sum forces, what is equal?
Main.
It equals the mass times the acceleration. And which way do you expect this thing to go up? Which way do you expect it to go up? I think we expect it to go up. So, MA is positive. Okay? You look at that equation, and you see two things you don't know. So you're not solving it. So you got to go someplace else. Where do you go next? You look at the torques acting on the pulley. Now, there's 4 forces acting on the pulley. The tension on the left, the tension on the right, the force of support, and the weight of the pulley itself. Of those 4 forces, which force or forces produce torques? The 2 tensions. The other 2 go right through the axis of rotation. Okay? Which tension produces the dominant torque?
The one on the right.
The one on the right. Okay? So on the tension on the right, to calculate tension, you need a force, but you also need a,
Radius.
so excuse me, not to calculate tension, to calculate torque. You need a force, but you also need a distance to that force that's perpendicular. The radius is perpendicular to the tension. So I have the tension on the right times the radius.
Isn't that negative?
It is negative. That tension would make this pulley want to turn how?
Clockwise.
Clockwise. So that would be negative. Okay? Then I have the tension on the left. It produces a torque. So I got the tension on the left times the radius. And it makes it want to go counterclockwise, so that one is positive. Okay? Anytime you sum up torques, what is equal?
I alpha.
I alpha. The sum of the torques equals I alpha. Okay? So we good now? Janae, you shook your head no. Doubting my work? You should. Something's wrong with the board. Nate?
I alpha should be negative because it's turning clockwise.
I alpha should be negative. Guys, you told me that this was the dominant torque. If the dominant torque is negative, I alpha should be negative too. Okay? So now we're good to go. We're treating this thing as a disc. That's what it says in the problem. It's a disc-shaped pulley. So we can substitute in 1/2 mr squared for I. For alpha, we know A equals R alpha. So for alpha, we can substitute in A over R. And over here, I want to just factor out of R. Okay? What happens here?
The R's.
The R's cancel. This R takes out the squared. This R takes out that R. And we're left with, minus the tension on the right plus the tension on the left equals negative 1/2 MA. The tension on the right, what is it? It's 25 newtons. If you pull on a rope with 25 newtons of force, that's the tension.
Plus.
The tension on the left, do you know a number for it?
No.
But you can come up here and you can certainly get an expression for it. The tension on the left is mg plus ma. Okay? Now let's do a little rearranging here. I want to bring my A's over to this side. MA plus 1/2 big MA equals 25 newtons minus little mg. I can factor out A. And lastly, I can solve for the acceleration. Okay? And knowing all the masses, we can plug in and we can get a value for A. Now, you guys know me, I really could care less what that value for A is. Once you get A, could you find the tension on the left? How? You've got it, you've already solved for it right there. Just plug it in real quick and you'll be done. Okay? So, I consider this problem done now. We were at the tension on the right, 25 newtons, the tension on the left equals that, and this is how you find A. But before I leave this problem, I want to talk about another little concept real quick. Is there, now, 25 newtons. I want you to look at this picture, and I want you to look at this picture. And tell me, is there a fundamental difference? Now, as soon as I put that up there, I had people saying no, and I had people saying yes. One thing's for certain, someone's right.
The acceleration's different.
Why would the accelerations be different? You're pulling down, that weight's going to pull down with a force of 25 newtons. What?
That weight has a moment of inertia and that force doesn't. Or the force in the first one doesn't have a moment of inertia.
I'm not, okay, well, you're using the wrong term, but you got the right idea. In the first one, you have a 25 Newton force acting because someone's pulling on it. Look at this equation. What do you see here? I'll give you a hint what I see. I see a little of that. It's not exact, but here's what I see. On top, 25 newtons minus little mg. The thing on top over there, what is it? It's the net force. That's the force making us go. That's the force resisting it. What do you see on bottom? I see the total mass of the thing moving translationally, and I see the mass of the thing rotating times what? Times 1/2. But what does that 1/2 represent? The moment of inertia coefficient. So here's the way this kind of works. It's the net force divided by the mass of things moving linearly, and you get partial credit, if you will, for things that rotate. You don't get to count all their mass, but you get to count some of their mass. When I add this thing here, I'm adding mass to the system. There'd be another term down here, and the acceleration would be less. Kaylin?
So if on a test we use, like, if we recognize the similarity, will we have to write out the whole thing again, or could we just?
Great question. Someone want to take a stab at answering it?
Probably just have to do all of this, probably would get credit for showing the physics, I guess.
It really depends on the type of question. If you're taking a multiple choice, if you're doing a multiple choice question, and you recognize that, by all means, skip to here, plug in, take advantage of your awesome physics knowledge. If it's a free response question,
I don't take a chance.
on you're taking a huge chance. On an AP exam, they like work. Okay, yeah, I know. It's not designed for you, Arjun. Okay, they like work. Okay, and sometimes they'll even put in key phrases like derive an expression for the acceleration using fundamental ideas. Well, if they tell you to derive an expression and you just plop that bad boy down, well, you can forget getting any credit. They don't care about you knowing the expression. They want to see where it came from. And also, think about this problem. In this problem we just worked, the question wasn't about finding the acceleration. What was it about? Finding the tension. So even if you knew this, that's a heck of a shortcut, but you still got to go back to there to get a tension. Okay? There's no such thing as bad knowledge, but you got to know where to apply it. Bottom line. Other questions? None? Yeah.
47.
47. Now 47 is the big brother of this problem. $47. An Atlas machine consists of two masses, M1 and M2, connected by a string that passes over a pulley. If the pulley is a disc radius r and mass capital M, find the acceleration of the masses. Okay? Find the acceleration of the masses. Now guys, if you really bought into what we just said, some of you could skip to the final answer right now. Okay? Further down, they say M1 and M2. They don't tell you which one is heavier. Okay? So, pick one. Doesn't matter. If you pick wrong, when you plug, if you had to evaluate it, things would just come out how? Negative. No big deal. Okay? So, skipping to the final answer, you got M1G pulling down this side, M2G pulling down this side. If we use the net force idea, if M2 is greater, M2G is the force making us go. M1G, does it help or resist us?
Resist.
It resists. So you subtract that. So on top, you have your net force. And on bottom, what do we have? M1 plus M2 plus 1/2 what?
Big M.
Plus 1/2 big M. Okay? That's the acceleration. Now, if you don't remember that, you're stuck writing some of the force equations. And guys, Some of you will remember this shortcut on Wednesday. A lot of you probably will make it a point to remember it on Wednesday. You are doing yourself a disservice if you couldn't set up those equations. Because, Mr. Cox might just put a question on the test that says, hey, don't solve it, but give me the sum of the force equations and the sum of the torque equations for a situation. Okay?
Is the test written yet?
So,
Is this just?
well, I want everyone right now to write the sum of the force equations and the sum of the torque and the sum of the torque equation. If you don't have it written down, try writing it. And let's call the tensions on this side T2, the tensions on the other side T1.
Mr. Cox, is this test on Wednesday like all multiple choice or half?
What? We're still in the development stages.
Oh, so then I don't have to.
So, summing forces. Okay, for 2, T2 up, M2G down, and M2 will be going down. Summing forces in the Y for 1. T1 up minus M1G down, M1 would be accelerating up. Summing torques. Dominant torque would be T2, T2 times R. It would make it go counterclockwise, so it would be positive. Okay, and then we have the other one, T1 times R. That would equal I alpha. The positive torque, the dominant torque is positive, so that would be positive. Okay. Is that it, guys? Does that match with what you put? From this point forward, you throw in a little A equals R alpha to get alpha in terms of A, and it's just algebra. That's all you got left. Okay? Yeah.
Okay. Since you have the torques going like, or the tensions going both ways, how are
Okay.
you
The
supposed
tension, the things above the pink line are acting on the disc.
Okay.
The tensions below are acting on the boxes.
Okay.
Okay, someone, we had a problem with this in the other class. Let me see if I think Mr. Miller stole my rope out of here. One of them. That's got about inside. Okay, but it doesn't matter. Look. Just sit straight. If I stretch this over your head and hang a weight on both sides, you feel a force going which way?
Down.
Whichever one is heavier.
No, but overall, both of them are pulling down. Okay? Tensions always pull away from the object. So the tensions are going to pull down on that. If I hang this bucket as a weight off one side of your head, the bucket's going to pull down on your head, right? Your head being the pulley. But the force on the bucket as it hangs there is going to be up, right? So that's how I can have those two tensions sitting in the picture going opposite directions.
Okay.
Okay, because on the pulley they do act down, but on the weights they do act up.
Okay, so you just have to think of forces as translational and versus angular. That's my problem. Because I was thinking angularly, like, because they both point up, but like one of them would be counterclockwise and one of them would be clockwise.
That the torques they produce, this one would be clockwise, T1 would make a clockwise torque, T2 would make a counterclockwise torque.
Okay.
Okay? Other question, Arjuna.
I was wondering, if the rope only slipped and didn't turn the pulley at all, would we get to go back to what we were doing before? Not
If it slipped with no friction,
okay.
if there was friction as it slipped, then you would still have unequal.
Tensions on either side.
Tensions. But we're not going to work with friction with ropes. Okay? Good? Okay, guys, let's do our quiz while you have time to really think about it.